Welcome to the third video for buckling. In this one we'll go through the effective lengths for several different boundary conditions that columns can have, and sort of the conclusions of what those tell us about their capacities. I said before that I would not make you solve the differential equation that is used to solve the Euler buckling equation. So d squared dx squared plus py over I equals 0. And I meant that, right? I'm not going to actually demand that you do that, but some of you might think about the general form, which is that y is equal to c1 sine square root p ei x plus some constant c2 times the cosine. Same. Oh no, I made it too short. You don't have to use that so much. What we're going to look at mostly, or indeed in this case at all, is we're going to look at the simplified solution we have for pinned. For a pinned thing, we know that for pinned the deflection at 0 gotta be 0. The deflection at L also gotta be 0, and that's going to mean that the cosine term has to be 0. Right, so we're gonna be able to simplify this out to y is equal to c1 times the sine of sine of the square root of p over e I x, because that first term right there, well, oh, not this, it means this can't be anything. It means that c2 had better be 0, because the cosine of 0 is 1. So we've got this much simpler equation to deal with. So, and that holds for if we have something that looks like this, where we've got a pinned top, and it should be, this should be a symmetric, right? Because it should be a sine wave, top and bottom. But that's not the only set of boundary conditions that we can have. If we have a fixed end, say we've got something like this, well, in that case, it's going to be straight, and then it's going to curve. But this is a bad drawing. So let's say we have, let's fix it right there. Then, if we have that, it's going to look like that. And if we just symmetrically draw another one down here, we're going to find that we get the same shape. But of course, this means that for this, our effective length, if we want to use this equation, if we want to use this, is equal to L itself, the same length, because this is the assumption that we use when we made this. With this one, this effective length, you'll notice, is going to be twice as long as the actual length of this column, which is only going to be from there to there. We can do this for any number of any set of boundary conditions. For example, if we have something that's fixed and fixed, it's going to come out straight with no slope, and then it's going to bow out like that. And we can pick out from here to here, it's going to act like one wave of this. And so that means that our effective length will be 0.5 times our total length. So what will that mean in relation to everything else that we've done? Well, it means that we can use these equations over here for non-pinned states. We just have to use the effective length instead of just the length down here. So we can still use this and these functions. We just need to use these effective lengths rather than the proper length. And what that's going to do is it makes this a lot easier. We don't have to worry about solving a new set of differential equations with different boundary conditions. But it also means that if we were to look at this with LE being 1/2 of L, that means that if we have a fixed end on either end of our column, we can have how far we are along this diagram. So we can get a substantial increase in strength from our columns if we fix them on both ends. Now that's difficult to do, but you can really make your column a lot more resistant to buckling. If we have one end that's just sort of like a flagpole just sticking up there with no supports, well, now we're going to double how far we are along this axis. And so we're going to be much more vulnerable to buckling if we don't have any supports at the top or bottom of the column. Okay, now let's get into sort of a more realistic example.